Hey, welcome back. This is going to be your first actual lesson on statistics. So let's go ahead and start from the beginning, uh, section 1.1. The first thing we want to talk about, of course, this whole chapter has to deal with data, how we analyze it, and really two main things here are experimental experiments and also observations. Okay, so these are really just two different ways that we get data. The first one, um, experiments. How do you know something's an experiment? Well, if it's an experiment, there'll be something called a treatment group and also a control group. Okay, one and two. Alright, so before I get to observations, let's talk a little more about these experiments. So here's the scenario. Let's say we're doing some kind of study on heart medication, and we're going to look and see um, if this medication actually helps prevent deaths um, uh, in these certain groups, I suppose. Maybe they have high blood pressure or something along those lines. We want to test this medication to see if this lowers their chances of increased risk for death. So let's go ahead and say that we'll look at some outcomes and we'll look at the groups. So two outcomes, well, they could live or they could die. Alright. Now, as far as the groups are concerned, we will say treatment and also the control. Well, the treatment and control groups, they are exactly what they sound like. The treatment is the group that's actually getting the medication. The control is the group that's not getting the medication. So whatever affliction they have, one of them will receive it. Let's go ahead and say that of the treated group, maybe there were 733 of them, and we'll say 692 of them lived, and 41 of them died. And then for the control group, let's say there were 742 of them, 682 of them lived, and 60 of them died. Alright? So, and we'll talk a little more about treatment and control group as well. Of course, the control group, it's really important to have a placebo, but let's save that just for a while. So this is your basic information here. You've got some data. This is called a data matrix, or you can just call it a table. We're not going to be too nitpicky here on names of things like this. The one thing that we will look at is some basic probability here. So what is the probability that the treated group, or the treatment, so people receiving the treatment die? Well, probability is really quite simple, at least in this case. It's just the number of what we want. So whatever we're interested over the total. Right? Probability is just a fraction. So typically we'll use this kind of idea. So here, what do we want? The probability, we only want the total in the treatment group that died. So let's go up here, we see the treatment. Well, we've got some that lived and died. And it looks like in the treatment group, 41 have died. So on the top we have 41. And the bottom, the total. Well, it's the total here, the total in the treatment group. We don't want the total in the entire study. So we're actually going to be using this 733. We're not going to be adding these two. So once you divide this out, you should get something 0.0056, or I'm sorry, 0.056. So what does this mean? If you have 0.056, once you type this in the calculator for 1 divided by 733, course, you can just change this to a percent by shifting this 2 decimal places, or 5.6%. So, probability that if they were receiving treatment that they would die, it was 5.6% in the treatment group died. So this is really, really simple stuff. Let's look at the control group real quick. So what about probability in the control? Okay, so same idea. We want the number of what we want over the total. So what do we want on top? We want the probability that the control died. So we find the control. We want them to die. Well, we don't. Well, we're interested in them dying. That's what we're looking at here. So we've got 60 of them there. And out of how many are in the control group? If you add these two up, we get 742. So if these things aren't provided here, of course, if you were going to ask to find the probability or percentage and the control group that died, you would just go ahead and add these up horizontally like this. Okay, so you do this division, you'll come up with 0.081 or 8.1%. Okay. All right, so that's very basic. As far as 1.1 is concerned, or chapter 1, we really won't get into probability too much, but just this idea of percents, and again, just what we want over the total here. All right. Now, let me at least take this time to kind of talk about treatments and control group. So in this case, we've got this heart problem, maybe some kind of blood pressure problem, some kind of ailment. Well, if you're given a pill, you've got some medication here. If you're given a pill, you're in there. If you're not given anything, well, then you're obviously not getting help, right? So, because you're not getting help, it's like psychological, I guess. Just because you're taking something makes you think that you're getting better. So it's really important that we have this placebo here. And that's the main method of control here. So a lot of times this ends up being a sugar pill, something along those lines. And that'll just help or control unwanted variants. Okay, so now let's look at observations. Observations, this is getting into section 1.2. Let's just look here for a second. We'll just look closer. Okay, so observations here, here's what I've got. Another data matrix here. I've just got these numbered, got 4 of them here, could be more, got some dots. What kind of types do we have? Well, we've got small, mid-sized, etc. Maybe these are different types of cars, these are the prices here. We've got miles per gallon and weight here as well. So here we're just looking at attributes of a car, okay? So the difference between an experiment and an observation. This is an observation study because there is no treatment here. There's no control group. There's nothing being applied here. In the past one, we were applying medication to see what kind of effect that would have. Nothing's being applied here. We're just kind of looking over some things, okay? And it might not always be so obvious. For instance, let's say we had gone to a hospital where some people were already receiving medication, and we wanted to compare 2 different drugs, or just compare, one kind of drug to no treatment. If we just went there and just kind of picked 5 at random that were receiving something and 5 at random that weren't, this would not be called an experiment. You have to actually, that would be an observation, because you're not assigning anyone to the treatment group. You're not assigning someone to receive something. So because you're not setting this thing up, it would be called an observation there. So it's subtle there. So you just have to look and see if you are setting something up. In this case, with the cars, you are not. All right. The next thing I want to go ahead and talk about are these. Well, actually, I'll go ahead and see. Next thing we'll talk about is, I guess, types of variables. There aren't too many of these. There's numerical and categorical, and then within numerical you have continuous and discrete. And we'll talk about this really briefly. So here's some kind of example. Types of variables. Let's talk about car type, right? Or brand, right? So you would start here. You'd say, okay, is it numerical? It's not, right? These are names, so these are categorical then. Right? Okay, so let's look at something else. How about maybe time? Okay, so you take time, numerical or categorical. This is not some kind of categorical. These are things like low, medium, high. They're really gonna have blood pressure or high at risk patients, low at risk patients. These are all categorical things. Numericals, of course, this means these are numbers here, right? And then the two types of numbers that we have, continuous and discrete. Time here is actually continuous. And just, if you're not familiar with these terms, continuous and discrete, say you think about a number line, 0, 1, 2, 3, I suppose the time that it takes to do something could be 1 second, could be 1.5 seconds, could be anything, right? There are fractions of seconds there, so could be any of these things in between. But as soon as we look at something like number of kids, well, number of kids, it can't be anything in between here, right? So because you can't have half a kid or a fraction of a kid. It can only be 0, 1, 2, 3. This is what's known as discrete. So the distinction between the continuous and discrete is this. If it can be these fractions in between, then it's continuous. And if it doesn't make sense, it's not possible to be these fractions in between these whole numbers, then we call that thing discrete. All right. So right, number of kids here, number of cars, right? Number of jobs worked, things like this. These are all discrete. Continuous time, temperature, you can have fractions of temperature, right? It's also continuous. And if you start with this hierarchy, you can't go wrong, right? You see temperature, you say, okay, categorical, numerical. It's numerical, what kind? Temperature, it can be these fractions, right? So it's continuous. Okay, so I think you get the idea there. Okay, so we are certainly interested in relationships in these variables. So in the last one we had car size, maybe miles per gallon with the amount you pay for a car. We would hope that if we pay more money for a car, we get better gas mileage. At least I would hope so. So we're interested in these kind of relationships. We want to go ahead and look at this thing called a scatter plot. I think your book has a pretty good diagram of these things. They've got these skull lengths here. So these are, I guess, our armadillo or some kind of animal skulls. I guess possum. Sorry. There's got some information here. We've got just the skull length and width, and we've got 104 of them, right? So over here on the right page, you actually see the plot of these things. These are actually, what's being plotted are these ordered pairs. So, I'm going to make sure it is skull length. So here, the skull length on the first one is, 94.1. So we have 94.1. 94.1, and the skull width is 60.4. So here you see the skull width is the y-axis, the length is the x. So we're trying to use the length of the skull to predict the skull width. So that's the idea here. So let's see what the length is 94.1. So pay attention to that. And the width is 60.4. So that's one ordered pair that's plotted. The next one, length, is being predicted. That's the x, 92.5, and the y is 57.6. And you would plot these things in the usual way, right? If I have 100 here, let's call this 50, and maybe this is 10, 20, 30, 40, 50, 60. Then you find this is 94.1, maybe about here. And then up to about a little above 60, right? Maybe about there. This next one is 92.5, a little bit closer this way, and up to about 57. And what they've done here is they've actually plotted all 104 of them for you. Of course, they use some sort of software to do this. They're going to do this all by hand. But the idea is you plot these things, width and length here. You would think that these things are related. But you make this thing is called a scatter plot. This is what we just went over. And you look to see if there's any kind of relationship here. So what you kind of notice is, it seems like there are these bands, right? There is this pattern here. All this information kind of falls in this general pattern here. So it sort of seems as the head length increases, the skull width increases. We call that an association. And we want to talk about the associations. Probably on the next page, yep. Okay. So the types of associations that are out there. What can two variables be? Well, they can be positive. Well, let's see if they're things could be associated, I suppose, or they could be independent. Okay. So examples of independence. I suppose maybe let's say we have the tails and the skulls. If we're looking at the tail length versus the head length. Might be kind of independent, it might be, someone could have a long tail but a small head, or a big head and a short tail. So let's say we have tail length and the head here. If it's independent, what it's going to look like is once you do the scatter plot, it's just going to be all over the place. There's no kind of pattern here. There's no sort of general kind of thing happening here. So there is no association here, and because there is no association here, these things are independent. And that's what it means to be independent, that one won't affect the other. So the things that are kind of independent, it might be like the kind of car you drive and whether you're male or female. It seems like one shouldn't really affect the other. You wouldn't really be able to predict. It would be all over like that. Let's look at some associations, types of associations. Okay, so we can have this sort of pattern happening, right? We call that positive, right? Why do we call it positive? Because it almost looks like a line, and if you have some algebra background, you know that the slope of a line that goes like this is positive. Or simply you can think about it, driving a car up here, you're going uphill, so this is positive association. As this gets large, this gets large. Like, driving this little car up here. It's going uphill, it's positive. Okay. You might have guessed negative is sort of a similar thing. So we have same kind of idea. You got your car going here. It's going downhill. This is negative. The two more things about these. These are actually special types of associations. We can even say that they're linear. So these are linear associations here. Okay? So we have a positive linear association and a negative linear association. There's something else that we could talk about called well, let me kind of draw this out and we'll see kind of what happens here. So let's say we have something along these lines. We say, well, is there a relationship? Well, there must be a relationship, and sort of looks like we have these kinds of bands going on, right? Most of our data falls between these bands, but this isn't a straight line, so I can't call it linear. But there's some kind of pattern here. It's not random here, so it can't be independent. So we call this thing curvilinear. Or I think people call it curvilinear. Should be. Yeah, okay. Yeah, we'll call this thing curvilinear. Alright, so those are the basic types of things that you can have with associations. You could have linear, if it's associated, or curvilinear, or maybe you might even see nonlinear. These are the same things. So again, even if I have something like this, is there a pattern here? This isn't independent. It's not quite random. Again, I still have these kind of confidence bands going on, so there is a pattern here, so I can't call it no association or independent. This has to be some kind of association, so we call this thing a curvilinear here. Okay. Alright, so that's pretty straightforward for those examples. Put this to the side for now. I guess we're going to go over some mean now. Yeah, let's look at just the idea of a mean. So, you've probably heard something along the lines of the mean. What is the mean? And if you're following along with us, this is 1.3. Okay? So what do I mean when I say mean? Mean is just sort of an average. So your book has this kind of thing. They use x bar for the mean. We'll get more in this terminology. And they call this x1 plus x2 plus etc. plus xn, all divided by n. What this stuff means, n is the total number here. And then these x's are just the observed data here. So let's say I had this data set, 0, 1, 4, and let's go with 3. Well, if I've got this data set, this is really your first data set, this is x2, this is your third data point, and your fourth data point. So that's how you would work this out. This is just notation for add them all up and divide by the total. So how many do you have? You've got 4 of them in total, 1, 2, 3, 4. So this is just 0 plus 1 plus 4 plus 3, all divided by 4. So what's your mean? Add this up. On the top you get 8 over 4. Divide this, 8 divided by 4 is 2. So your mean is 2 here. Okay? We will get into some standard deviation as well. Yeah, I think now is probably a good time for that. Alright, so what does this mean? Let's kind of let me draw kind of a picture here. Let's see, so this is data point x1, this is data point x2, x3, and x4. 1, 2, 3, 4. Okay. So x1 was 0, right? That's right there. x2 was 1. X3 was 4. and x3 was, I'm sorry, x4 was 3. Okay. So what's the mean? The mean is sort of this average. It was 2 here, so we'll draw this kind of dotted line. So this is this horizontal line that's closest to all these points. Alright, well, you can have a lot of means like this, right? You could also have, alternatively, I could have just had 2, 2, 2, 2. This has the same mean. 2 plus 2 plus 2 plus 2 is 8, divided by 4 total is 2. But it looks different. This one varies a lot more than if they were just all 2, right? So the next thing we're going to look at is this thing called variability. We call it, a real creative name, variance. So we kind of want this idea of, how bad is it? How bad is our mean compared to these data points? Well, this is your mean. This is your x bar, right? Well, the difference here is x1 minus x bar, right? And this is x2 minus x bar. So 1 minus 2. This is 4 minus 2. And this is 3 minus 2. So we can find these differences. But if I were just to add these things up, and your book kind of makes this point as well, x1 minus x bar, x2 minus x bar, x3 minus x bar, x4 minus x bar. If I were just to add these things up, this is what 0 minus, I guess I don't have very much room, but 0 minus 2 is negative 2, 1 minus 2 is negative 1, and 4 minus 2 is positive 2, and 3 minus 2 is positive 1. So, if I just added these things up, the unfortunate thing about it is it won't tell me much about the variability. You would add this all up, you would get 0. But I want all these distances. I want some kind of idea of this. So, what they came across was, well, I could take the absolute value of these things and say, well, this total distance was positive 2 plus positive 1 plus positive 4 plus positive 1. And add this all up, you get this positive number. Or the other thing is we could do is we could square it. We won't go into why they square it, but there's some nice properties occur if we use this squaring notation instead, or convention rather. Alright, so here's what we'll have. It's really x1 minus x bar squared, at least with this problem carrying this on. x2 minus x bar squared plus x3 minus x bar squared plus x4 minus x bar squared. And this is all going to be divided by, well, there's two formulas here. I'm going to show you, let's divide it by 4, just for this one. This gives us something called the variance. And it's got this Greek notation. So this is called sigma, and this is a squared symbol. So this is sigma squared, alright? Alright, so it's as simple as that. So just as recall here, we've got 0, 1, 4, and 3 here, and we want to use this formula. Let's go ahead and apply it. Okay, so again, recall the mean was 2. We found all of these things actually on the side here, right? 0 minus 2 squared plus 1 minus 2 squared plus 4 minus 2 squared, and then plus 3 minus 2 squared. All over 4. Alright, so what do we get? Negative 2 squared plus negative 1 squared plus positive 2 squared plus 1 squared, and then this is all divided by 4. Alright, so we have what? Positive 4 plus 1 plus 4 plus 1, all divided by 4. And what do we get? We get 10 divided by 4, or 2.5. Okay, so our variance here is 2.5. This gives us an idea of how much our data points vary from one point to another. Okay, so really you can kind of think about this is the formula here, and the actual formula, if you call this thing n, your book has this divided by n. The way this formula works, think of it as this is the error between the mean and the actual points, and you're kind of taking an average of the errors here. So that's what the variance is. All right. Of course, we squared all these things. So, let's say we were dealing with feet or something. We'd end up with square feet. But we were looking at the variability in feet. We don't measure that in square feet. So we have this other thing called the standard deviation. And the way we get from squared feet back to feet, you take the square root of this thing. So the standard deviation is just the square root of the variance here. This is always the case. Anytime you're asked to find the standard deviation, you just take the square root of the variance. It's as simple as that. And what's the symbol for it? Just sigma. So the relationship is really quite nice. You've got variance, which is sigma squared, and standard deviation is sigma. So if you know these symbols, and I give you the variance, and I say find standard deviation, you know this guy. Well, how do you get that? You take the square root of this, gets rid of this square, right? And that's exactly the definition here, right? If I give you the standard deviation, I want the variance. Well, okay, well, how do we get from this symbol to that? Well, I just squared it, right? So, the conversion is just either you square it or take the square root to get from one to the other. It should be quite simple. So here, this is just the square root of 2.5, which is 1.58, or 1.5811, and it goes on. This is good. Okay, so both give us an idea of what the actual variability is there. Your book doesn't quite have a formula written out for you. So let me go ahead and take the time to do that now. Alright. So if you're asked, we talked about the mean, we know the mean here. What about the variance? So we've seen this variance is sort of this thing. There's two things here. This is x1 minus x bar squared plus x2 minus x bar squared, etc. all the way up to x and minus x bar squared, all divided by what? N. So that's your variance there. And then if you wanted just the standard deviation, if you just want a standard deviation instead of variance, take the square root of both sides. So you get the symbol for standard deviation and this ugly mess on the right hand side. So you just fill in all these things and compute that. Okay, so unfortunately there's one last thing, kind of fine point there as far as what to use where. I don't think I want to get to it just yet. We'll come back to this in a bit. So I'll keep that off to the side. Alright, so there's a couple other ideas here. So the mean gives us some kind of idea of where the center is. We've got some kind of idea of where the center of the data is. We call this thing central tendency. Right, so mean is a good idea there. We have other measures of central tendency. And then the standard deviation and variance are both ways to look at variability here. How much is it going up? How much is it going down? A high number in variance means there's a lot of change from one data point to the other. Um, in fact, if you actually calculated here with this 2, 2, 2, and 2, if instead we had that sort of thing, you do all this kind of subtraction, this minus 2 squared plus this minus 2 squared plus 2 minus 2 squared plus 2 minus 2 squared, you get a bunch of zeros you add up divided by 4. That's 0. The variance is 0. It's because there's no variance there. They're not changing from one to another. It's just constant 2. So higher numbers mean more variability, and if you have 0, there's no variance. It's 0 is as low as it can get. The variance is always positive, or at least non-negative, and 0 just means a straight line. They're all the same number. Okay. So let's see if I can't flip the page. We'll use these same numbers, 0, 1, 4, and 3. Alright, so there are these other things out there. We're going to talk about this thing called the median and the mode. Actually, I might have to give another data point here. Let me squeeze one more in here. Let's say we have 2 3s. Okay. So the median is another kind of measure of tendency. Here's what we'll do. Median, we put these things in order. We have 0, 1, 3, 3, and 4. That's the first step in finding the median. The median is just the exact middle. So we see we have 5 points here. 1, 0, 1, 3, 3, and 4. So we find the middle one. It's this one, right? So this is your median. Your median is 3. Not bad, right? As far as this, the mode, you don't have to put in order. We just look. 0, are there any other zeros? No, right? 1, are there any other 1s? Nope. 4, any other 4s? Nope. 3, we have 2 3s. So we see 3 is the one that happens the most often. And that's what this means. So, most frequency, or highest frequency. So here is mode is also 3. Alright, let me give you another data point, or another data set, I suppose. Let's look at 1, 4, 4, 5, 2, and 7. Let's do one more. Let's call it 1. Okay. 1, 2, 3, 4, 5, 6, 7. Alright, scratch that. We won't do one more. We'll scratch that out. Let's change this one, however, to another 2. There we go. So 1, 4, 4, 5, 2, and 2. Okay, so let's find the median of this thing. First step, we got to put these things in order, right? So let's go ahead and write that out. 1, 2, 2, 4, 4, and 5. It's a good idea to check. We got 6 here, we got 6 there, so they match, right? We didn't leave anything out. Alright, so let's find the middle one. We've got 1, cross out 5, cross out 2, cross out 4. If I cross these 2 out, there is no middle. It's right there, right? So what happens in this case, this was nice. We had this odd number, so we cancel out. There is actually a middle. We call it the median. If this happens, what you do, you take the average. So it's not even very, it doesn't even sound that intense, right? It's just sort of, well, it's not there, close enough, right? We'll take the averages and add them up and divide by 2. Right? There's just 2. So this is 6 divided by 2, or just 3. So the median here is 3. Alright, let's look about the mode. So what happens the most? Okay, we've got 2 2s, and we got 2 4s. So what's the mode? Well, we call this thing bimodal. It's got 2 modes. So this is bimodal, with 2 being the mode and 4 being the mode. Alright? This one we call unimodal, because there's one mode. And your book kind of has these things called histograms. They're not very, they're pretty easy to understand, I think. We got 0, 1, 2, 3, and 4. So for this data set, 1 and 2. So we've got 1, 0, something that looks along those lines. We've got 1, 1, which is about like that. We've got no 2s, we've got 2 3s, and we've got 1 4. So here we see the mode here is just the tallest one. So if I gave you this sort of thing, with this being the frequency on the left side, 3 is the mode, and we call this thing unimodal. Right? So you should be able to know just from the data set, seeing which one occurs the most frequently. If I give you this histogram, it's just as simple as which one's the tallest. It's there. What was it? It was 3. Alright, and let's look at this one. So we've got 1, 2, 3, 4, and 5. Same idea. 1 and 2. Alright, so we had 1, 1, right? We had 2 2s, right? We had no 3s, so no 3s, right? And 2 4s. And 1 5. Okay, so you look at this thing, if you were asked to find the mode from this kind of thing, we look for the tallest peak. These peaks are equal. So you can kind of see, yes, this is bimodal here. There's 2 peaks here. And your book kind of makes a good point for this as well. Let's talk, let me pull this over just for reference here. So this is more, this will give you a good idea. Go ahead and read this, and you can kind of see this should be pretty much similar to what we were talking about. They do talk about these the skewing. To kind of better clarify, this is unimodal. It's got one mode. It's right in the middle. It's nice and symmetric. You know, it's if I reflect it on the left and the right, this is nice. We call this thing. This is not skewed. So not skewed. Yeah. So I'll have to erase this, I guess. This one below it, we call this thing right skewed. Sometimes in the book, it may reference it as positive skewed, but here's the way to remember it. Where's the tail going, right? This thing is stretched out to the right, so it's called right skewed, right? It's almost like I took this thing and I just stretched it way the heck out to the right, yeah. Well, if I did it the other way, it would be left skewed. So if I had flipped this, it'd be left skewed. And again, the other terminology, positive. To the right we have positive, so right skewed is positive, skewed mean the same thing. And if I had it shaped the other way, then I would have left skewed or negative skewed. So these are terms that you should get familiar with. I don't think we'll be well, yeah, we will use these terms pretty frequently. All right, so we've covered quite a bit: mean, median, mode, standard deviation, and variance. Right? I don't think your book talks about range, but that's certainly another idea to measure variance. All right, so let's look at these box plots, quartiles, and medians. Okay. So let's move on to 1.3.5. So I know we kind of jumped around and gathered a few things around in that section, but let's go ahead and pick up with 1.3.5. You're following along. All right. So what do we got? Alright, so IQR. This is really a good idea. It's just kind of, we call them outliers. We want to see if there are any kind of outliers. So if I write down some data points, 2, 3, 3, 1, and 17,000. Okay, so something happened there, right? Um, so this seems very extreme. It's kind of an outlier, so maybe we can look the other way on this. And really, it's kind of frowned upon to throw these data points out. We won't be doing any serious statistics in here where we're actually throwing this out and recalculating anything. We're just going to be classifying something as an outlier or not. And there's a really nice way to do it. It's not very tough. But first, let's get an idea of what a box plot is. Box plots will help us kind of visualize data. Let's see here. I don't have an example written down, so let's just go with this side here. All right. So box plot has to do with the median. Another idea for the median, it is the middle one. We could also call it the 50th percentile. It means that 50% of the data lies below it, and 50% of the data lies above it. It seems to make sense, right? Works exactly right here, right? And that's why you have to put these things in order, right? That way you know that half of it lies below this, half of it lies above it, where this is 3 here. Right? We'll take the average of this. And then the same thing here, right? Up below and above it. Alright, so box plot kind of does the same thing, but we have 4 different categories. It's not just 50%. We have 50% is the median. We also have 25% and 75%. Okay? And then we have this these 2 endpoints here. We'll talk more about these endpoints in a little bit. Okay, so this is the median. Let's talk about these things. So let's go ahead and use our data set here. What do we have? 1, 2, 3, 4, 5. Let's make a new one. 1, 2, 5, 6, 8, 9, 10. Okay. So if this is our data, we want to find the 50th percentile, 25th percentile, and 75th percentile. Alright, so here's what you do. You want to find the median first. So again, we've already put these in order, so there's nothing to do here. If I were to cross these out one at a time, I see that there is no exact middle, right? The middle is be right here. Right? So the middle is right there. It would be 5 plus 6 divided by 2. So this is what, 11 divided by 2, so you get 5.5. So 5.5 is the median, right? So now what happens is you take what's left of this. So you take this part. So now you treat this like 1, 2, and 5. We'll find the median of this thing, right? We're taking half the data that lies below this thing, and then we're finding the median of that thing to get the 25th percentile. So you just take the median, everything to the left of it, is this, find the median of that. Here it's 2. Right? So this is the, just to clarify, 50th percentile, the median, and this is 25th percentile, the first quartile, we call it. And what's special about this too is it means that 25% of the data will lie below this, or equal it. Okay, so you can do the same thing up here. Let's take this 6, 8, and 10. Let's go ahead and find the median here. The median here is 8, right? And this is called the 75th percentile. Okay? Alright, so what does this box plot look like? Well, we'll start with the 1. The highest one is the 10. Alright, so we have this this 2 here. So we've got maybe a 2 is about here. So we've got this 5.5. Maybe 5.5 is about here. And then we've got this 8. Alright, so these are special. We call this the first quartile. Again, it's not a very fancy name. Quarter, right? You break it up into fourths. So a quarter of the data lies below it. Second quartile, 2 quarters lie below it. Third quartile, 3 quarters lie below it, right? Alright, so these are our 3 quarters. We draw this box like this. And then we draw a line through the center. And we just connect these dots. So this is what a box plot might look like. The advantage of this, the really nice thing about this, it gives us an idea of what our distribution looks like. So I can look at this thing and I can tell, okay, is this right skewed or left skewed? I can look and see, well, is this thing right skewed or left skewed? Again, it's just sort of, this thing's left skewed, right? You get this long tail here, and it kind of drops off here to the right. Right? So wherever it's elongated is how it's skewed, right? And it's very slightly left skewed. It's almost symmetrical, right? The symmetrical line would be right in the middle. Okay, so I think we've covered this fairly well, at least what a box plot is. Now, your book goes into one other thing as far as using these for outliers. So, sort of the idea that, yeah, if I had 1700 here, you might have something that looks like this. You've got the point out here, 1700. They've labeled this as an outlier. So if you see this in the book and you see this, they've figured out this is an outlier. So they rewrote these fences, cutting it out. So it's visually shows that essentially this is the distribution minus this guy. Okay. Well, you can't really just say, well, that's really high, so that's an outlier. You do have to be kind of sensitive with this stuff. You know, it could be very, very close. So, we have a way of doing that. IQR. Let's talk about the IQR here. And, actually, I'll do this on another page completely. IQR, this stands for interquartile range. This is in your book. It's in a nice box thing here. They write this, Q3 minus Q1. What does that mean? This is the third quartile. This is the first quartile. So this is where 75% of the data lies below it. This is where 25% of the data lies below it. And if you're looking on a box plot here, you know, something like this. This is the first quartile. This is the third quartile. 1, 2, 3, and then 4. 100% of the data lies below that. Right? Okay, so call it interquartile range because you're just taking these inner quartiles and just subtracting them. It's as simple as that. All right. All right. So here's what you do. Let's find some. Let's take a nice data set here. 1, 2, 3, 5, and let's go with let's go with 8, and then also 17. 1, 2, 3, 4, 5, 6. Okay. All right. So let's go ahead and use this, and we look at this and we see 17. Okay, is this an outlier? It's really high compared to these. We cannot just say yes, it is, or no, it isn't. So here's the idea. Let's first find the IQR. Eventually, we're going to find this thing called an upper fence. I'll write this now, so you can just write this and see where we're headed. Lower fence. Okay? So the upper fence is the third quartile. So you just take this bit. And it seems like if we're finding an upper fence here, we should do this plus some kind of constant of this IQR. So they actually do Q3 plus 1.5 the IQR. The lower fence, well, You take this lower guy. This is Q1. It seems like we should be going to the left sum, right? So this is actually minus 1.5 IQR. So these are our formulas to find the upper fence and lower fence. And the idea is once we find these fences, we look and see if the data point we're in question of, if it lies inside. If it lies inside, it's fine. If it lies outside of these upper fence or lower fence, well then it's an outlier. Okay. So first of all, we have to find the quartiles here, right? So the middle, there isn't a middle, it's right here. For this, we actually don't need to find the second quartile. It's 4 here, right? But we can split it. So Q2 equals 3 plus 5 over 2, which is 4. We'll take this data set and the one above it. Okay, so Q1, it's the center here. It's 2, right? Q3 is going to be 8. So these are the quartiles. Alright, so let's find the IQR. It's just Q3 minus Q1, right? So in this case, it's this 8 minus this 2, right? 8 minus 2, 6. So this is our interquartile range. Alright, so now comes this part. Well, we have to take these points, and we actually have to find the upper and lower fence. Let's do lower fence first, okay? So lower fence, it seems like you start with Q1, and we're going to go left some. So we actually are going to subtract some off, right? So let's find the lower fence. Q1 minus 1.5 IQR. Okay. So lower fence is, we write this in as 2 minus 1.5 times 6. Right? And I put these parentheses here. This is really just the order of operations here. You don't really need to write that. It's implied. Alright, so you have 2 minus 9, which is equal to negative 7. So the lower fence is negative 7. So I can already look at my data set. You know, this negative 7 is way out here. All of my data lies above that, so I'm not going to have anything too low. But that's not really what we were questioning anyhow. Let's find the upper fence. Alright, upper fence is Q3, so we start higher, right? And then we're adding some kind of multiple of the IQR, which happens to be 1.5. Alright, so Q3 was 8, so 8 plus 1.5 times 6. This gives me 8 plus 9, which is actually 17. So 17 is right on the cusp. So it doesn't actually lie outside of this, so it's fine. It's not actually an outlier. It's kind of a weird one. I didn't actually intend for it to be so close. But let's kind of just look here. Yeah, 17 right there, right? Negative 7 is way over here. So comparing this, none of the data points are actually outside of these fences, so there are no outliers here. Had we instead found that the upper fence was 16, the upper fence would be here. We'd call this an outlier, and the box plot would show that. We'd put the 16 here, we'd label this here, and just put a dot for 17. And then, of course, if it was larger than this, if the upper fence was 20 or something, then it's fine. They're all good as well. There's no outliers there. Okay, so I hope that kind of explains the concept of box plots and outliers, and how we can use box plots to give us an idea of the distribution of our data here. So we can see if it's positively skewed or negatively skewed, which again is just right skewed or left skewed. Okay, we're skipping this section here on transformation. We're not going to do any transformations here. Don't worry about that. Categorical data. We're not really doing anything with bar plots and proportions. You might want to go ahead and read through that section though. It does kind of go over proportions, you know, this percentage thing we went over in the very beginning. That's a concept that you're going to have to get really used to, because we're going to use that number of what we want over the total number. We're going to use that a lot. Okay. Other than that, I think we have this. Okay, yeah, we're almost done. I don't know why I tell you that. I guess you can look and see how much time we have left on the video. Okay, so if you flip open to 1.5, this is where we're actually coming back to this idea. I call this a population. 1.5, actually, they have a really good drawing here, where they have this, they call this the population here, and this is the sample. Now, typically we're dealing with samples here, so what we did earlier with the standard deviation and variance, this is actually an averaging from the population, which typically we don't have, right? You know, think about how hard it is to sample everyone in the U.S. That would be a population. It's called a census, right? And actually, it's anytime you sample everyone in the population, it's called a census. So that's convenient. All right, so they've drawn maybe a lot of cars. Maybe these are all the cars that maybe Mitsubishi produces, and we're interested in the gas mileage there. So it's not realistic to actually go to every single car that they've ever produced and see and test them to see what their gas mileage is. Right. So what you end up doing, you take some samples, right? So we take this sample over here in Jacksonville, and we take this sample over here in California, and we take a couple over here, and we just take a couple of random samples. The key there is we do need it to be random. There can be some problems when we don't pick these random samples. And we like to observe them. So any kind of process like this, we're observing data, right? It's not an experiment. We're just pulling things out. We're not throwing anyone into a treatment group. Okay, so just to clarify, so this population, it's very unrealistic because you're trying to actually pull all these things. A lot of times these things could be several thousand or even millions, and so it's just unrealistic to, one, do all the data. You need some kind of computer to help you out with this computation here. So what you end up doing is you end up usually finding some sort of sample. And so the sample is actually slightly different. It is a type of averaging. So up here I have the standard deviation. Let me write the variance out. So this is sample variance. Sample variance looks like this. You've actually got x1 minus x bar squared. It starts out the same way, all the way up to xn minus x bar squared. And you divide it, instead of dividing it by n, which is the total number you have, you divide it by 1 less than it. Right? So if you actually go back, so where did I put that page? We actually computed this one earlier. We divide this thing by 4 because we had 4 data points. You do the exact same computation, only instead of dividing by 4, you divide by 3. And typically, that's the one that we'll use. Actually, let me correct this notation. Let me actually write this as s squared. So your sample variance, we write s squared. For population variance, you write sigma squared. So you write Greek letters for population for whatever reason. So these are the Greeks. I don't know what's popular about the Greeks, but that's just notation there. All right, and then same idea. So if I have the variance here, the sample variance. Once I want that, I want the standard deviation, sample standard deviation. You just take the square root, right? So it's all the same exact mess all over n minus 1. And that's all there is to it. So that's the only distinction. But most of the time, more often than not, your calculations will look something like this. We'll know if we've gotten something from a population or a sample I think in your book, anytime you have a problem like this, it's going to tell you it's coming from a sample. Um, Very rarely is it coming from a population. So if it doesn't tell you and you can't surmise it, more often than not, just use this one. You're probably right. Okay, let's talk about different types of variables and how they can have effects here. Uh, so again, remember we have all these types of variables. They could be discrete, continuous, or they could be categorical, right? There's a lot of things going on there. And what did we say? We started out doing this comparison between experiments and observations. So experiments are really good to draw conclusions from. We set this thing up, we see, okay, well, the treatment worked, or the treatment didn't work, so there's no real difference. And we'll look later on how to tell if it's significant. It looks like here, well, yeah, the treatment, 5.6% versus, what was it? There is a difference here, right? But is it significant? If I just did the control group again, maybe it's a different percentage that die, right? For all different types of reasons, right? Some are at higher risks, different blood pressures, things like that. And we'll talk about ways to actually fix that. But let's look at some of the dangers here as far as sampling. So now we're talking about observations, right? The sampling, talking about observation. So here's the danger here. You cannot take anything, you can't actually conclude much from observations. They're the easiest to do, there's not a whole lot of work, and in the clinical field, you'll see there are a lot of observations for ethical reasons, more so than actual experimentation. But here's a good example. So using sunscreen, this is just bad use of sampling. Using sunscreen causes cancer. Alright? So how crazy is that? How does that happen? You look at the data, sunscreen causes cancer. Don't use it, guys. Alright, so what happened here? Well, it's not that using sunscreen causes cancer, but there's something in between. It's just sort of, from our data, we didn't take into account this thing called a lurking variable. So we call this lurking variable. Well, what's happened here? Well, it's the people using the sunscreen. People use more of it. Maybe they're out at the beach a lot more often, so they're in the sun more often, so they have more sun exposure. So it's not that it's the sunscreen causing it, it's just that because people are out in the sun more, they use more sunscreen. And it's not really taken into account, it's the sun exposure causing the cancer, and not really the sunscreen. So the lurking variable here is sun exposure. So whenever we design these things and actually do our studies, we want to be careful of these lurking variables. As far as sampling is concerned, there's really three main types. You've got the basic one, random. So sampling. There's random. It's draw numbers out of a hat, draw names out of a hat. Evens are in the treatment group. Odds. Well, I guess this could be experiments, right? I could do this for an experiment too. Evens are in the treatment group. Odds are in the control group. Or maybe as far as random sampling, with the Mitsubishi, I pull ID numbers out of a hat. Just randomly generate ID numbers, and whatever city that is, I call them up and we do a test on that car. So that's random. It's, I think, most intuitive way to go about it. We have something called stratified sampling and something called cluster sampling. Okay, stratified sampling, here's the idea. Well, if I want to look at some blood pressure medication and I want to see how well it's working, it's a good idea to look at, you know, low blood pressure, regular, and high blood pressure, right? Or maybe, we're testing, heart medication, and it matters what the blood pressure is. This just happens for a lot of different medications. So the idea is you would look in the low, and you would do random sampling there. You would look in the regular, you do a random sampling there. And you look at the high, you do a random sampling there. So you do a random sampling at all of these. I think your book uses the example of you have a baseball teams, you want to know the average salaries, so stratified. You would actually take each baseball team and you would say, well, let's split it up into baseball teams instead of just picking random people, and we'll kind of get the average value, or we'll do some sampling from the Yankees, we'll do some sampling from the Marlins. Yankees, I'm sure, is going to be larger, right? Cluster sampling is really the same idea. The only difference between these two is with clusters, you don't necessarily sample every single category. So these are the categories you've got, and that's really the only subtle difference there. Okay, so let's move on to experiments. So controlling all this stuff in 1.7 should be fairly straightforward when we're looking at experiments. Controlling, yeah, we're trying to look for the things that you don't really account for. So watch out for the lurking variables, things that could get in the way. Your book uses this nice example of let's say we're doing this medication or something, and causes dehydration or something like that. And we want to see if it works or not. And we're not really interested that maybe the dehydration has some effect on side effects or overall outcome. So we don't really want the dehydration to be one of these lurking variables. We want to get rid of that. So maybe you can control that by when you take this pill, you drink some water or something along those lines, and then it's not the dehydration. You kind of eliminate that variable. So anything that can happen and maybe would affect it, you just want to eliminate other variables if at all possible. Randomization. Of course, we want to randomize. It depends on the way we randomize. Of course, this could be very biased, depending on the way you randomize. Of course, if I do a political poll right out of the convention center for the Democrats, obviously the poll is going to be a little slanted, right? So make sure that your randomization is actually random and not just very local here. The more widespread is better. Let's see, replication. The idea is the more we have, the better. It's as simple as that. The more we have, the more accurate we can say things. Blocking. Again, this is just a simple, sort of like a stratified and cluster sampling. Blocking is just taking into account that it might matter when we're actually doing these tests on these people. So in this case, let's say we were actually doing a treatment group for this medication, the blood pressure. We have a high blood pressure, middle blood pressure, and a low blood pressure. It's going to make a difference, right? So the blocking there is really high blood pressure, regular, or I guess regular, and then low. So that's the kind of idea with blocking there. So all these things can kind of help improve your experiment, and these are good things to use in your experimental design. you can kind of see here, this is a nice picture that shows the use of blocking here. So we've got a number of patients, low risk and high risk is. And they've got the colored dots. You can see they split them. And then within those, they actually do the random sample for each one. All right, so that's pretty much it. Reducing bias, just using placebos, kind of things like that. Go ahead and do those recommended homework problems, and now hopefully you should be ready to do the quiz. All right. Well, good luck, and thank you for tuning in.